Hi everybody, I hope you're doing all well. This is Math 262. This is the first video lecture and it's going to be about simultaneous diagonalization and an example. So these video lectures are intended to be just to support the lecture notes but not to replace them. So to make most sense of this lecture, please read lecture notes off. March 24th first. So I will not repeat everything there, but just this is some example which I help will elucidate some of the fine points. So the central result in these lectures was the following theorem. So I'll just quote the statement. This is the theorem about simultaneous diagonalization. So the setup is as follows. Let V be a finite dimensional vector space over a field F. The field is not important here. And suppose you have a set of operators on V. The curly A is a set of operators on V with the following two properties, such that, let me write that below. So these are the conditions now. So for, any two operators inside the set commute. We have Ti, Tj equals Tj, Ti. So they commute. That's the first condition you want. And the second condition is that independently each of these is diagonalizable. Okay, these are the assumptions. And what the theorem says is, if these are true, then you can simultaneously diagonalize them. So then there exists a basis B for V such that all operators in the set are simultaneously diagonal with respect to this basis. So they are represented by diagonal matrices. Okay, so this theorem, let me push this up for a bit. This theorem and its proof is in the notes. So I will not reproduce the proof here. That's best read, I guess, from the notes. Now, what I want to do is to do some concrete example. How to find the spaces in some simple setting. Now, well, there's a sort of payoff here. If you have a too small example, it's not really interesting. A very big example is not easy to compute. So I try to choose something in between. So here's how it will go. So let me push this up now. So here is the example. Now, an important point, if this is going to be true for operators, it's going to be true for matrices. So, I mean, if you fix a basis when you start, then all of these operators will be represented by some matrix, and this condition for operators to commute translates as the matrices commuting, and the diagonalizability translates as the matrices being diagonalizable. Now, so here's the example. Suppose your field is real numbers. And let's select V to be R4 four-dimensional space. Okay, fine. So here are the two matrices. These are going to be 4 by 4 because they're operators, so they go from R4 to R4. So A, let me choose it to be 0, 3, 0, 0, 3, 0, 0, 0, 0, 0, 0, 3, and 0, 3, 0, 3, 0. So it's a very sparse matrix with a few non-zero entries, so that will make the computations easier. And B is likewise some kind of permutation matrix actually, so 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, okay. Now, I claim that's these two matrices. So, okay, what's the curly A? So the curly A, if you want, as a set of matrices is AB, or if you're not comfortable with matrices in this thing, they're the operators whose representing matrices with respect to, let's say, the standard basis are these two matrices, okay? Now, the first thing to check is this commutation property. Is AB equal to BA? That's a direct computation. Let me write the results, but of course you have to do it yourself just to make sure. So AB turns out to be, well, where does this 3 hit? This is the last row, so this is going to be 0, 0, 0, 3, etc. You make all the computation. It turns out to be this one. Please check. And BA does really give the same result, but this has to be checked again. Okay, so I'll leave that checking part to you. Now, are these two matrices diagonalizable? That might not be obvious when you start with two arbitrary matrices. We'll see this on the way, and we'll see that they are diagonalizable on the way. So we'll see that A and B are diagonalizable. But maybe I should make this remark. There's something we haven't proven yet. That will come in the future, I hope. So real symmetric matrices are always diagonalizable. That's a theorem. And if you just borrow that theorem for a moment, you can immediately decide that they are diagonalizable. But again, we didn't prove that. So, but let me write this as a remark. So symmetric real matrices are always diagonalizable. This is a non-trivial theorem. We'll prove it, I hope. So, but that sort of gives some guarantee here. Okay, sorry, I couldn't fix this yet. Okay, let's go on. Now, the problem is, okay, we have A and B. How to find a single basis for V such that both A and B are diagonal when you make this change of basis. Okay, so let us start by finding the eigenvalues and also the eigenspaces of A. All right, so we have to do this determinant A minus lambda I, the good old stuff. So it looks like this: minus lambda 3, 0, 0, 3 minus lambda 0, 0, and this here. So 4 by 4 determinant, but it's not going to be difficult since it's kind of block form. So I mean, you have the product of the determinants of these two blocks, and it's not hard to check that this is going to be lambda squared minus 9 parenthesis squared. So if you collect the like factors together, so you'll get lambda minus 3 parenthesis squared times lambda plus 3 squared. Fine. So the eigenvalues are, there are two of them. Three and minus 3. So far, so good. Okay, what about the eigenspaces? Well, we have to do this one by one for each eigenvalue. So for lambda 1 equals 3, you need to solve A minus 3I times V equals 0, right? Well, this is funny, but this is supposed to be just a zero vector. Okay. Now, of course, this leads to some linear system. Right, so it's going to be this linear system, minus 3, 3, zeros, then 3 minus 3, 2 zeros, 0, 0, minus 3, 3, and finally this one. Well, the right-hand side of the equation is 0. Well, we can immediately row reduce to, let me not write the details of the row reduction. This is 1 minus 1. Well, this second row will be completely eliminated, and if you bring up the third row and sort of normalize it, you get 1 minus 1, and all rest are 0. So the matrix has rank 2, and there are two free variables. The solutions are vectors of the form k, k, l, l, where k and l are just arbitrary real numbers. So these are all the solutions of the system. Well, all vectors like this except the zero vector are the eigenvectors. And if you want to write the eigenspace, let me denote by W3, 3, because the eigenvalue is 3. Well, it's a set of all such vectors, but let me write it a little bit differently. It's the span of, let me write a basis for it. It's the span of 1, 1, 0, 0 and 0, 0, 1, 1. Okay, so it's a two-dimensional subspace of V. Fine, we found this eigenspace. I hope everything's all right so far. So let's do the same for lambda 2 equals minus 3. For lambda 2 equals minus 3, you just do an analogous computation. This time you need to solve A plus 3I V equals 0. So your linear system is this one. Well, I forgot the zeros here. Let me put that quickly back. Again, by row reduction, can reduce this all the way to here. Okay, again, this matrix has rank 2, so there are 2 free variables left, and the solutions are okay, they are of the form k minus k, l minus l. Okay, so let me write the -3 eigenspace here. It's the span of 1 minus 1 0 0 and 0 0 1 minus 1. Okay, so just to summarize, we found 2 eigenspaces, each of them 2-dimensional, and that sounds good because the total dimension was 4, so 2 plus 2 is 4. So these were eigenspaces for A, so the matrix A. We didn't use the second matrix at all so far. If you just wanted to diagonalize A, well, it's simple at this point. You would choose a basis for W3, you would choose another basis for W minus 3, put them together. That's going to diagonalize A. What about B? Now, this fundamental fact, so maybe let me write, what about B? This fundamental fact is you could see this in the proof of the theorem, which I didn't write here, but it is in the notes. Is that W3 and W minus 3, the eigenspaces of A, are B invariant. Okay, this is sort of the key thing. The sort of half of the proof. I mean, you prove that these eigenspaces are invariant under the other operators, and then you do some sort of induction. What does that mean? So if you select a vector in W3, hit it with B, it may not be an eigenvector, but it's going to land again in W3, the same space. If you pick a vector from W minus 3, you hit it with B, it's going to land back in W minus 3. It cannot go out. Okay? Now, so multiplication by B induces operators from W3 to itself and from W minus 3 to itself. Okay, that's the fundamental fact. And the rest of what we have to do is kind of hidden here. Well, these are 2-dimensional spaces, so find eigenvectors inside here for B and eigenvectors inside here for B. For two generally given matrices, you would have to do kind of quite a bit of operations. Well, you have to write the general element here, multiply by B and see if that's a multiple and so forth. That would take time. In this example, let me just observe some eigenvectors directly just by using the simplicity. So observe that. There's a little bit of cheating, but I think it illustrates the point. So observe that if you multiply B with 1, 1, 1, 1. Well, let's remember what B is. It was this permutation matrix. Well, if you multiply a permutation matrix with a vector, it just changes places of these entries, and since they're all equal, it will give you back again 1, 1, 1, 1. So 1, 1, 1, 1 is an eigenvector of B with eigenvalue plus 1. Fine. And the nice thing is, this is inside W3. Why? Well, remember the description of W3. It's up there. It was vectors of the form K, K, L, L. In this particular case, K is equal to L and that's equal to 1, but that's fine. This vector is inside W3. Fine, so we found one eigenvector just by direct observation. In general, this step might be more difficult. I mean, you would have to make some computations. But anyway, so we need another, because W3 is two-dimensional, we need a second eigenvector to finish the job. So the second is not very different. You just have to do this. 1, 1, minus 1, minus 1. Let me not do the multiplication explicitly, but you can do it easily, of course. It just changes places again, and changes places in the following way. Minus 1, minus 1, 1, 1. Okay, fine. Then this means this is minus 1 times the original vector. So this 1, 1, minus 1, minus 1 is an eigenvector of B with eigenvalue minus 1. So that's good. So, I mean, this says our job is done with W3 part. So we need to find some kind of similar thing for the second eigenspace, W minus 3. But maybe before we go on, notice that, I mean, just these are not any arbitrary vectors in W3. If you pick something else in W3 like 1, 1, 0, 0, that wouldn't work, right? So it's kind of important that these work. Okay, now on W minus, okay, sorry, on W minus 3, okay, this time again with some experimentation, B times 1 minus 1, 1 minus 1. Again, if you look at what this permutation matrix is doing, just changing places of first and third components and so forth, you see that you get the same answer. So we found, and yeah, so what were the elements of W minus 3? They were of the form K minus K, L minus L. So this fits right in. So 1 minus 1, 1 minus 1, which is first of all inside W minus 3, is an eigenvector of B with eigenvalue plus 1. And there's one more left. Similarly, B of 1 minus 1 minus 1, 1. If you do that, this vector again belongs to W minus 3 and it's independent of that one. Just it's easy to see. Again, by direct computation, you have this. And this tells 1 minus 1 minus 1, 1, which is again in W minus 3 is an eigenvector B with eigenvalue minus 1. Fine. So yeah, that's sort of all that we need. I mean, we found 4 vectors. They're linearly independent. They were eigenvectors of A initially because they came from eigenspaces of A, and we checked one by one that these 4 vectors are eigenvectors of B, so that's very good. So now, finally, putting it all together, we get, putting these together, we have this curly B, which is representing the basis. These 4 vectors, the first 2 for W3, the last 2 for W minus 3. This one, yeah, so what's the significance of this basis? So with respect to P, if we make a change of basis from the standard basis, both operators will be diagonal. Or if you prefer to say this purely in terms of matrices, that just means the following. So you cook up your change of basis matrix P, as we usually do. The columns are these basis elements, they representations with respect to the standard basis, which is themselves. So 1, 1, minus 1, minus 1. Just side note, this is a cool matrix. This is like a Hadamard matrix, but that's another issue. Okay, so this is your P, and if you do change of basis using this P, I want to show P at the same time. And by the change of basis formula, you have P inverse AP is, well, you have the eigenvalues, so 3, 3, minus 3, minus 3, and the rest is all zeros. And the order of these is about the order of columns, right? So the first 2 are eigenvectors for 3, the last 2 columns are eigenvectors for minus 3. Speaking of A, this is just for matrix A. And for B, you have a similar expression. This time it is 1, minus 1, 1, minus 1. The first vector was a plus 1 eigenvector for B. The second was a minus 1 eigenvector, then a plus 1 and a minus 1. The rest are zeros. Okay, one basis diagonalizing both at the same time. So that's the point. So notice that, well, the eigenvectors are common for both, but the eigenvalues are different, right? So these are 3, 3, minus 3, minus 3, and these are 1, minus 1, 1, minus 1. And the eigenspaces are also different. So here, the first 2 would span an eigenspace for A. In this one, the first and third would span an eigenspace for B. So, the eigenspaces are not exactly the same. Yeah. So I hope this example illustrates a little bit what this theorem is saying. It would be very good to go back now again to the lecture notes and read them once again by looking at this. Okay, that's all for today. Thank you very much for listening.